Hey everyone, welcome to Wednesday's class. Alright everyone, welcome to Wednesday's class. I'm doing this online for the reasons I mentioned on Monday. I need to spend a little bit more time with the family. But I am always hesitant to cancel class because that's just money out of your pocket. And I know it's probably in the past you heard, oh, class is canceled. A faculty member says, well, I'm off to a conference, or I have a deadline, I have a grant deadline. You were like, whoopee. But this is no different than a personal trainer basically canceling on you but billing you, right? And you've already paid me, so you have been billed. I don't think you'd be okay with that at all, even though you don't necessarily like what the personal trainer is going to make you do. So I'm hesitant to cancel class, and this is the best alternative I could come up with. So I appreciate your tolerating this, and remember that faculty who try to make it seem like you're getting a gift by them canceling class really don't care about you, and I want you to know that I don't either.
Oh no, wait a minute. Which one did I say? I said I did or I didn't? Which one is it, man? Those are not remotely the same thing. Oh man, this fentanyl stuff, I tell you, it really, oh no, it's back again.
Okay. Anyway, all right. So we're talking about electrochem, the middle of chapter 9, right? Maybe we'll talk about the beginning of chapter 9 if we have a little bit of extra time. But this is the middle of chapter 9 on electrochem. And I begin the chapter, today's lecture is very qualitative. We're going to talk about batteries because batteries are very important to our alternative energy future. Around 2050, it's predicted that the last oil well will be dug, the last new oil well. That's called Hubbard's Peak. What that means is that it doesn't mean that the world runs out of oil. It means that as every oil well dries up from that day forward, there will not be a replacement. The world economy is going to do a serious freak out when people realize that, and you'll be around to see some of that. I'll be gone, but just barely, so I'm kind of glad about that, to be honest. The government has been talking about what kind of alternatives you could have to replace it, and we actually have a lot of those. It's mostly going to be solar and wind. Not so much hydro. We've already dammed every river. That's not a joke. We've already dammed all the rivers. No more hydro. But wind has got a lot of potential, and of course solar. So actually the government used to think about hydrogen. So we would burn hydrogen as opposed to petroleum. And that is not looking so good. All right, the reason is because if you're going to drive a car with hydrogen gas, you have to have a fuel tank. And if you recall, hydrogen has a high compressibility factor, right? Its pressure is more than it should be. So that means you have a hard time to put it into a gas tank, like a gas cylinder like you see in the hallways. You can't actually put that much in because the container can't hold it. You can't really liquefy it unless you freeze it, and how are you going to put that on a car? So lots of problems with hydrogen fuel. Instead, what we could do is use wind and solar to just charge batteries, and then batteries, if they can run your car and run your home, then what we need fuels are for things like airplanes and ships. And unfortunately, the airplane and ship thing is kind of a big deal, and a lot of government policy people are not sure how we'll deal with that, even if the rest of the country is electrified. These are the kind of things you learn in grad school, by the way. So if you're interested in learning more or becoming a part of the solution, to be frank, you're not going to do it at this level. You need to go on to grad school. Okay, anyway, read the chapter if you want to see the nuts and bolts. But today I'm just mostly, when it comes to electrochem, mostly going to talk about batteries because that's the most important thing. I'm going to be pretty qualitative this lecture, and on Monday I'm going to be quantitative with calculating battery performance, but I'm not even going to tell you what that means right now. And then Wednesday's lecture will be a little bit of a mop-up. Maybe I can tell you a little bit about solid-state thermodynamics because batteries are actually solid-state materials. Catalysts, we do need better catalysts. We need to make the fuels that we have go longer. Catalysts are good for that. And anyway, so maybe we'll get a little bit of solid-state thermo, which is actually the beginning of chapter 9. Maybe I've written that in the wrong way, but anyway, okay, electrochem. What about electrochem? Okay, so again, this is going to be about batteries, and technically delta G is the maximum work that's not pressure volume type work. So all the work that you can do that's not from a magic cylinder. So what does that mean? Well, it means electrical work, because work is defined as like anything that could lift a weight. And so I know that I can get an electric motor to raise a weight. So that's a type of work. And so to analyze that, I need to analyze delta G, because again, that's an example of non-PV work. So if you recall, this is good practice for, notice I got a new pen. Oh God, I gotta remind myself. Okay, BDP minus SVT. Okay, as promised, ever since we got past chapter 5, everything's at constant temperature and constant pressure. So if we're at constant T and P, then the question is this equal to 0, right? So what the heck are we doing anything with delta G? And if you recall, the answer lies, I actually did this to you before we were starting to talk about Hess's law. We actually have the chemical potential, right? So we have chemical potential times change in moles. And then I can tack on to that other types of work, right? So electrical work, let's see, stretching a rubber band, that was part of one of your test questions. And so this is why it's applicable to batteries. All right, now to relate delta G to a battery, let me just go ahead, I shouldn't tell you this, I'm going to tell you anyway. What we really want to do is know the voltage. Okay, so I've previewed what we're going to talk about for the next 10 minutes. Okay, to do that, before I get to voltage, I want to think about energy from chemical reaction, but now it has to be like an electrochemical reaction. So what about electrons is energy, and how do I relate energy to chemistry? Right, so that's the goal for a couple steps I'm going to do here to do that. Okay, so point 1 is that to relate electrons to energy and then to a chemical reaction, the first thing to note is that energy is extensive. Let me write that. Energy is extensive. Okay, so I'm going to need to relate this to the number of electrons. So therefore, what you need to know is that this little, what was that little nu? I don't remember. Nu is the number of electrons. So I know I was geeky enough that I tried to learn electronics when I was in middle school, high school, and grad school. I can calculate the voltage drop across a resistor, but when it came to a capacitor, then I was completely lost. I found understanding circuitry to be impossible, but I do remember that the power in a circuit is current squared times resistance, or what is that? That's voltage times current, right? And so I'm going to need to relate energy to number of electrons. Okay, so the next thing is what kind of energy does an electron have? Right? What can an electron do? And the only thing about an electron, it has a really low mass. I don't think there's a lot of kinetic energy there. It does have charge, though. So what I need to do is now relate energy to charge. Of course, charge will be related to the number of electrons. The more electrons I have, the more charge I have, right? I think that's kind of obvious. And of course, energy is extensive. That's point number 1. So point 3 is now I'm going to relate that energy to the change in Gibbs energy of a reaction. Per mole. You'll see why per mole in a minute. So sometimes you just maybe take it for granted that everything's per mole. A lot of things have been per mole lately, but there's a special reason why we're going to do everything per mole when it comes to electrochem. All right, so in terms of how do we now think about the energy that an electron or new number of electrons has? Its mass is low, but I can't really think of much that it can do other than move. So, but what is a moving electron but a moving charge? What is moving charge but current? And remember what I said the power of the circuit is? It's got I squared R. Almost forgot there for a second. I is current. Current squared times the resistance of the circuit. So a flowing charge has got to be a form of energy. So let's see. Let's start. We're going to do a little bit of equations. Not too many. It's mostly qualitative today. Okay. So what I'm going to do is multiply the number of electrons times Faraday's constant. Okay. And I think these are basically simplifications of what are called Faraday's laws, which I put in the textbook, but I'm not quite doing it the same way because this makes more sense to me. Okay. So F is the Faraday constant. And that is equal to the electric charge. The electric charge of an electron times Avogadro's number. Okay, now an electric charge has units of coulombs. So let's write that down. Here, I'll write that above. Okay, and that's not a derived unit. That's like a kilogram. You don't derive it from something. It just is. And there you go. Okay, so next thing to do is again relate that to energy. And so I'm gonna do this. Gives change in energy, right? Okay. So there's a slight problem here in that I've got something that's basically joules per mole, and then I've got technically something that's related to the number of a mole of charge. The charges of charges for a new number of electrons. So I don't think that's energy. So how do I make the units work, right? I've got joules per mole, and I've basically got coulombs on the right side, number of coulombs. And you'll see what this new will come from the analysis of particular reactions. Most reactions produce just one electron. Some produce 2 and 3, but for the most part, we don't really need to worry about this. So this is just basically coulombs. Okay, to make this work, we're going to multiply this by E. And what is E? Okay, so E is going to be called the electromotive force. Okay, an electromotive force, I hear the word electro for electron motion, so that's like current. I've already said ad nauseum how current's related to energy via power. Force is what makes it move. And I can see that it's basically going to have units of joules per coulomb. A capital C is a coulomb. And I believe that the number of moles works itself out because from here to here, I guess that's per. Like yeah, Na is like the number per mole. So there's per moles on the right, per moles on the left. So all I have to do is figure out how to turn coulombs to joules. And so all I have to do is multiply that by something that has units of joules per coulomb. Right? So it's kind of cheap, but it works. But what is it? What is E? I mean, you can't just... it's not like, so here's the takeaway. I once set you up in a similar situation with the PV equals NT using Boyle's and Charles's law. Hopefully you remember that. You do have a final coming up soon. And what we found is PV was joules and N times T was moles Kelvin. So the units didn't work, and so I just said, oh, multiply it by a fix-it factor, which has joules per K per mole, which is the gas constant R. And that actually only comes about because the way we derived units were not consistent with nature's laws. If you, I'll show you how to do this in 346 if you're interested, but if you use the right units for everything, then there would be no gas constants. That 1 over 4 pi E naught in Coulomb's law, which was awful in physics 2, it doesn't exist. It's the number 1. The mass of an electron is 1. So there's all kinds of different systems of units where there are no constants. Okay, the electromotive force is not like that. It's a real thing, right? So it's not like the gas constant. I don't know why I talked so long about that. So what is it? All right, now we got to think about, you probably know quite a bit more about what make electrons have energy than you realize because, well, maybe you haven't seen this device before, but one of the oldest technologies we have is called an electron gun. In fact, before we had flat panels, and you're not that young, you probably saw those old cathode ray TVs, those big thick things, and that's what I grew up with personally. Those are electron guns. So they have electron guns that hit a phosphor, and they have phosphors that phosphoresce at different colors, and that's how you get a color television. Okay, the way the electron gun works is it's actually a light bulb. So here's a filament. So that's plugged into the wall. So I'll just draw a little plug there. Okay, of course it's under a vacuum. The whole thing is under a vacuum, and this, of course, has a bunch of electrons. And the funny thing is that, and this is kind of silly, but in a vacuum, electrons can just fall out of the wire. That can actually happen. But to make sure that it happens, what you do is you have here you have a little plate. So what I'm going to do is I'm going to add a little plate, and I'm going to give it a real powerful, let's say a kilovolt plus, right? So electrons are attracted to it. If it was negative, they'd be repelled. I'm going to make it plus. Okay, then the neat thing you do is you drill a little hole in it. It's not the best looking hole, is it? I didn't draw that very well. That bothers me. Here, I got to do it again. Oh, I know what I did. I know what I did wrong. I actually have to practice this, by the way. There we go. Okay, that's a pretty neat looking hole. Okay, literally a metal plate with a super high positive voltage and a hole in it. Now, what happens is the electrons are super attracted to the positive charge, and they start moving real fast, but they end up just shooting right through the hole. And there you go. So now the electron has built up tremendous kinetic energy, and that bothered me. The electron needs to look good. There we go. So the electron just shoots right through the hole, and of course it strikes something. And of course, if this is your television, this would be the phosphor screen of an old cathode ray, and that's how it works. The point of this is to note that that your EMF is voltage. Now, if that confuses you, I just showed you that you hopefully just kind of know this from your physics 2, with just your knowledge in general, that electrons pick up energy from voltage. But you may be wondering, what about, voltages are in volts. What about joules per coulomb? Well, voltage is in volts. But did you know this? A volt is a joule per coulomb. So there you go. Voltage is your missing factor. Okay, the only thing that's really kind of stupid about this is that why aren't we using the letter V? I don't know. It would be a lot easier to do this and a lot easier to remember, I'm sure, if we use the letter V and not the letter E, but I don't get to choose this. You know, I just realized that if enough people use my textbook, I can start digging around with conventions. I can start changing them. Because if everyone uses my book, then I get to write the conventions. So it's chaotic good, right? So I would upend everything, but I mean it for the best. It's called the Daenerys Targaryen rule of ethics. So there's one last thing here. There's one last thing, and this is also going to be kind of strange, is that there's a minus sign. So why minus sign? Okay, you got to write that. Here, let me make that look better. That bothers me a bit. Okay, equals minus. Okay. Why the minus sign? Let me write this up here. So minus sign, why? Because, okay, this is a strange thing to write, so make sure you put this correctly in your notes. I can't write all this out. And this is no joke. Ben Franklin is largely considered to have discovered electricity. Now, that's, in my opinion, kind of crazy. I mean, Ben Franklin did a lot of really cool things. Supposedly, he was really a horrible jerk. If you knew him personally, you wouldn't like him at all, according to everyone that knew him. I mean, he's, you know, we don't have any video of him, right? So we don't really know. But even if you look at like scientific writings back in the 1700s and all that, people credited him with discovering electricity with that whole key on a kite thing. It turns out Ben Franklin thought, you know, now he knew that something was moving, you know, this thing that jolted him, and so he, you know, so electrons, let's just call them electrons, because he didn't really have any reason to, you know, like, is it positive or negative? That's kind of arbitrary, right? I mean, what we only know what up is because of gravity, but nature doesn't really feel gravity. So, like, why X and Y are different than Z is a human convention. What makes things plus or minus, again, is a human convention. Nature doesn't know what plus and minus signs are. So Ben Franklin called electrons positrons. He thought electrons were positively charged. And that mistake has never been corrected. So, in fact, even if you are an electrical engineer, my understanding is that they formally teach you to analyze circuitry in reverse. Because the convention of positive electrons is so ingrained in our technology that even electrical engineers, because a positive electron simply moves in reverse of a natural electron, but you can still understand everything just fine. It's still flowing charge. This is simply one of the craziest things I know, but this is how it's done. Okay, again, because Ben Franklin had the charge wrong, you have to put a minus sign, because the other geezers, I shouldn't say geezers, but anyway, those other geezers, like, you know, Hess and all them, they did not get their facts wrong, right? So positive gives energy, negative gives energy, that stuff is right, but to make that mesh with voltage, you have to put a minus sign because all the electrical people think that electrons are positive. So that's absurd and ridiculous, but that is how it works. Okay, next bit is, let's put this together with what we recall from like chemical potentials and all that, and we have to talk about equilibrium, constants, and all that stuff you just had a test on. So sometimes I think about doing this part right after Hess's law, because it actually works pretty well. At the same time, with equilibrium constants, it's kind of natural to go into talking about solution phase thermal, so I never know which one to do next after we do Hess's law. Okay, anyway, okay. So I have the reaction is equal to this stuff, so let me just expound upon that. So we know that the delta reaction G per mole is going to be the Hess's law thing Remember, that's what that little knot means. That's the standard temperature pressure. So back when we were doing reactions, that means that the chemical is by itself. So when you were doing Hess's Law back in high school in your freshman year, you never took into account mixing, and that's why reactions with positive Hess's Law delta G's can form products, because that doesn't take into account the in-between spaces. Right, that's your Hess's Law is only products minus reactants. But what about when you have a mixture, right? And that was an answer to one of the questions on the third exam that, to be honest, almost everyone missed that. So that was very sad. Okay, so, Hess's Law, something, something, plus RT, Ln. Now, I'm not going to use the letter K, and I warned you about this when I first introduced equilibrium. I told you, oh, by the way, when we do batteries, we can't talk about equilibrium in batteries because a battery in equilibrium is a dead battery. So we'll talk about battery design, and that'll be very clear in a little bit. So when you are not at the end of a reaction, but at the beginning, or really anywhere not at the end of the reaction, we use the letter Q, the reaction quotient, instead of the reaction equilibrium constant. For various reasons, I'm not going to make a big deal of this, and you'll understand in a minute. Okay, and this, of course, again, is equal to minus number of electrons. Now, as we get to chemical reactions, some reactions produce one electron. Most reactions are going to produce one electron, some two, some three. So that's where that comes from, and that will be more clear in a little bit. And F, and then remember E is actually the voltage. So those are multiplied, so those are not minus signs. Okay, now from here, I can now solve for E, which brings me to a big point here. Let me see here. Delta R G per mole over Faraday's constant minus RT ln Q over the same constants. Okay. Now the reason I'm working this the way I'm working it is that what we really care about in electrochem is to know the voltage. So before, we had data tables that would give us Hess's Law numbers that we could use to calculate how efficient our reactions were, what their yields were. We could figure out how to manipulate them. When it comes to electrochem, that's not so important, because the reason it's not so important is you don't want your battery to go to equilibrium. You want your battery to always be at non-equilibrium. You want your batteries to be fresh. You know, I'll never forget when I'm out among normal people, I always hear all these rumors about how to make your devices last longer. Oh, you should charge them up and let them charge all the way down, and then charge them up and let them charge all the way down. That's absolutely wrong. That wears out your battery in a big, big way. You always want it to be fully charged. So, anyway, so voltage is the thing we care about, and that's what we're trying to calculate. All right, now remember that we have something akin to a Hess's Law calculation. And so we're going to call this E naught. So all of these factors are going to go into something called E naught. And I'll just write all this stuff again. Okay. And E naught is called the standard. Okay, so I'm gonna use an acronym EMF. That is the electromotive force. That's just the voltage. Okay. Now let me cut to the chase. I don't have too much more to talk about here, so maybe we'll end a little early. But what we're going to have are Hess's Law data tables where instead of delta G's, we're going to have EMFs. Now, the reason is because you're going to have, just like when you do Hess's law, right, you always have to have at least two equations to work with, right? So you have, like, all right, I want to burn octane with oxygen, and I'm going to make CO2 and H2O, right? So that's how, like, your car engine works. And you're going to be given information on, like, formation energies and all that. So you have to do a little mixing and matching, and you always have to have at least two equations to work with. So this stuff is the same, but since they're electrical, they're like redox active. If you think about that table in chapter 6, it was just a bunch of formation energies. It was just carbon, coal, and hydrogen gas going to make octane, hydrogen gas, oxygen gas going to make water. But the electrons are not really, it's not like you're gaining or losing electrons. Everything is probably neutral. Okay, when it comes to batteries, your reactions, your basis set, that's the word I used back when we were on chapter 6, they involve things losing or gaining electrons. So they don't really belong in the same data table. You could put them in the same data table, it's just weird. So you have a different data table for your Hess's law type calculations when you're doing electrochem, again, because electrons are being shed and lost. And you also can technically, the number of possible, like the size of the data table is extraordinarily large when you're talking about electrochem. And that's because if you're talking about, just some simple molecules or an ion like zinc, really take anything in the D block, right, metals. Those things are very redox active, right? That means that metals can exist in multiple oxidation states. And that means that the size of your Hess's law-ish data table with EMFs can be extraordinarily large because zinc can lose one electron, it can lose two electrons, it can lose three electrons, right? Each one of those types of reactions is its own entry. So that's why I'm saying that these data tables can be way more expansive and a little harder to read as a result. Okay, now I'm about to start to talk about those reactions, but before I do that, what I want to do is calibrate you a little bit on what this EMF means. All right, so to do this will be our only calculation today. We're going to do a ton on Monday. In fact, you're going to get kind of sick of it. So that's why I'm trying to do as little of this as possible. All right, to understand what an EMF is, let's do this. Let's say that a reaction has, okay, so this would be like zinc shedding one electron to become zinc plus, 1 plus. And let's say that there is a strong push for that of minus 100 kilojoules per mole. Okay, minus means it's spontaneous, it's very downhill. Now, at this point, I hope that you would have enough horse sense to know that minus 100 kilojoules per mole is very, very powerful, right? That's akin to burning gas, right? That is a lot of energy being shed. Okay, so under that context of knowing that this is a very powerful reaction, what is E naught? So E naught would be, okay, I already wrote this, but I'll write it again. So this is minus 100,000, so I'm in standard SI. And again, the number of electrons, that would be 1 per, so that's 1 per mole. So I have per mole on top, per mole on bottom. And then the Faraday constant, again, remember that was Avogadro's number times the charge of a single electron in coulombs. That would be 9.65 times 10 to the 4 coulombs. Oh, sorry, no, sorry. I already screwed up. The number of electrons is just the number of 1 It's the per mole. The per moles get canceled in Faraday's constant. My bad. Right. That's where it is. Sorry, I screwed up. All right. So what's this equal to? This is equal to roughly, approximately. I mean, you can see for yourself. Approximately 1 volt. Okay. So here's one of the things that's kind of interesting about electrochem. You probably thought 1 volt. Well, that doesn't sound 10,000 volts. Well, that's a lot. Oh, no. 1 volt is a lot. 1 volt is quite a bit. So that's one of the reasons I bring this up. When it comes to electrochem, a reaction that can generate a volt of potential EMF is a really good one. If you had an easy way to, say, get to voltages around, say, 1.5, that would be a very, very big deal. Now, the reason I'll explain next time is because then it wouldn't be too hard to turn water into hydrogen gas and oxygen gas. Now, I already mentioned that that's not necessarily, in terms of a fuel, there's problems, right? Because again, hydrogen's hard to store, but if there was an easy way to make it, we probably would figure that out. There just really isn't. So 1 volt is a lot. If you can get to 1.5 volts, and again, I'll explain more in the next class, generating hydrogen would be very easy, but it's not, because again, this is a very, very downhill reaction. And again, as I'll talk about next time, water just doesn't fall apart. I mean, there's plenty of hydrogen right there. Water doesn't want to fall apart really at all. It's actually a very stable molecule. Now, one reason for that stability, by the way, is because, okay, H2O. So there's your H2, there's your hydrogen molecule, which is a good fuel. Okay, what about the oxygen? Oxygen doesn't come in the form of O atoms. It comes in the form of O2, and water only has 1. So that is actually a really big problem. If you're going to use electricity to split water, the hydrogen isn't a problem, it's the oxygen, because you've got to pair it up with another oxygen and involve O2, not O atoms. That doesn't make sense. Okay, the next thing to talk about is when it comes to this part, between today, I'm going to tell you, we're going to end with just talking a little bit about how batteries are designed, and mostly about batteries. The next class, we're going to talk about example after example about what goes inside batteries and how you determine the voltage of the battery. And if I was to do another lecture, we could talk ad nauseum about the reaction quotient, which would be how the battery, fresh out of the factory, what are inside of it, what are the activities, right? I have to use the word activities, it's all condensed phase, that give you a certain Q that then affect the voltage. Personally, I consider that an engineering issue, and a battery that's well engineered, this doesn't change much until the battery dies. I mean, if you think about it, your batteries don't really just wind down. If you have a 9-volt battery, it doesn't just slowly, 8, 7, 6, 5, it doesn't just slowly drop in voltage. When it goes quickly. So electrical engineers design the innards such that this is actually kind of constant, but of course everything stops eventually, including people. So that's why I'm not really going to say too much about this part. I would have had another lecture, but again, for those of you chemical engineers, take a class on this, right? This is kind of not really what we care about in terms of just, I care more about describing what voltage is than necessarily how to make a battery last as long as possible. Okay, all right, now we're going to get into battery design in just a little bit about what's in the battery that gives you voltages that I'm going to say for Monday. But a little terminology. Now you may notice if you actually look at Chapter 9 that there's a lot of discussion on terminology, but electrochem, for physical and analytical people like researchers, the electrochem people are kind of their own group because they have very different words and concepts that the rest of us never really are concerned about. So one of those things, now this isn't particularly hard, but I'll give my generic A and B. Okay, so A is something that gets reduced. And of course, where did that electron come from? So the way you want to think about this is, where did that electron come from? Something has to provide it, and that is the process of oxidation. Okay, another thing to note is that oxidation is like, remember I told you this about the word adiabatic. There's many, many definitions, and that's very unfortunate. We have the same word for different things, and that causes so much confusion. What a great thing, huh? All right, oxidation, the word implies that something reacted with oxygen. That is a legitimate definition of oxidation. But when things react with oxygen, they generally had lost electrons in the process. So that's what oxygen tends to do to things. So often, sucking an electron out of something is done by oxygen. So often these can be the same thing. So maybe this electron was shed out of molecule B because it reacted with oxygen. The problem is that that doesn't have to be the case. So two different definitions, but they're related. So in other words, it maximizes the confusion possible. So one thing is mnemonics. I'm not going to test you on this, but hopefully, this isn't hard to remember, right? Going negative reduces you, and oxidation does the opposite. That's just one of the mnemonics. I just Googled it, but anyway. Okay, so we care about voltage. Here's your, you notice how much it looks like our little chemical potential? And by the way, that's why everything is per molar here. As I'll explain on Monday, we're going to, voltages, right, where are they? It's a joule per coulomb. Now, coulomb is our new per molar, right? So since we're talking about electrons, we're not going to talk about per mole, we're going to talk about per coulomb, but a coulomb is a mole of electrons. So notice that voltages are chemical potentials. So, anyway, I forgot why I'm talking about that. So with that, yes, that's just reviewing what we were talking about. So we talked about why we cared so much about voltages. And now, I've hidden this. I spent nearly an hour drawing these different devices. These are very crude representations of batteries. And one of the things I saw this little Nature Discovery show talking about, people had an idea about electrochem long before Ben Franklin. And it's thought that like the pharaohs, the ancient Egyptians, who, remember that, all those pyramid stuff, that's like 2000 BC, right? Not 2080, 2000 BC, which is hard to imagine. Like Cleopatra is closer to us in time than Cleopatra is to the building of the pyramids, which is pretty nuts. Okay, so back in those pyramid times, people were mining copper and zinc and stacking them in between, and using wet pieces of paper or papyrus to separate them. And someone noticed that if they touched it, they got a shock. So it's thought that those were the first people to basically discover electrochemistry. Although I'm sure they thought it was a god of some kind, like zapping them. Maybe it was. Okay, so here's our first attempt at a battery. So we have a solution and two electrodes. That's what I've crudely tried to draw here. And let's do copper and zinc. And they're both sticking in solution. So this is our first attempt at a battery. Okay, now here's what's going to happen. The zinc, if you do this, is going to oxidize, right? So it lost electrons. It oxidizes. Now, a piece of metal has the elements in that said metal in the zero oxidation state. You can't have a chunk of something, a solid piece of metal, where all of the constituent atoms have charge. It would explode. I mean, it would explode faster than the speed of light. Coulomb's law it says that they're repelling each other, right? So positive, negative doesn't matter. Atoms in a metal bar are neutral, and that means oxidation state of 0. So if zinc is oxidized, then it's going to have to go from the solid metal bar to an aqueous salt. So it's, zinc salt. Okay, now the way you can tell is that the zinc electrode will corrode. Okay, copper, and again we know this because we have to simply do this. Copper is going to go from the aqueous solution to, it's going to do that with 2 electrons. This is shedding 2 electrons. I should include my electrons. Okay, so copper, so we have to have zinc and copper salt in the solution. Copper is copper is plating out, so the copper electrode is getting bigger. The zinc electrode is corroding. And again, you can see this by eye. Now, there's a giant problem, though, with this battery, is that as soon as you stick the electrodes in, you might get a shock, but it's going to stop. Now, the reason is that if you look at this part especially, the metal bar here, it's getting bigger. This is shedding. The big problem is that the current can flow inside the battery. So if this is a battery, there's something missing here. There's a wire, right? And now for you nerdy kids like me who wanted to learn some electricity when you were in middle school, you know that a load, which is like your car or your battery or your whatever, whatever you're trying to drive with electricity, is represented by a little squiggly line, which represents resistance. Whatever, that's fine. For our purposes, we're going to have a voltmeter. Regardless, we need a wire that connects the 2 electrodes, but the electrons don't care about that, right? They're basically short-circuited. So the zinc is shedding electrons, and they're just plating right onto the other part. So it's short-circuited. So this is pretty much useless. You cannot really build an effective battery this way. Okay, solution is to put some kind of barrier between them. Okay, and what is that going to do? Okay, a barrier. All right, so the electrons again are being shed by the zinc, but they can't get through the barrier. All right, so instead, so instead they're now going to go through the wire. And you have a current meter, a voltmeter, something that tells you that. In fact, one of the more important things is to know is that the electrons are going from the zinc to the copper side. Okay, next problem. Without more information, I look at this and that battery is not actually going to work very long. That's going to die really quick. Now the reason is that as electrons shed off the zinc, you have charge being lost here and gained over here. So over time, the right half of this barrier, remember the job it is to prevent a short circuit, that's just like insulation. The problem is that if you're moving electrons from the right to the left half, you're going to build up a positive charge here and a negative charge there. So now why are the electrons going to want to traverse? Right? Electrons like positive charge. So if this builds a positive charge, the electron could go this way or it could just go back. Right? It's happy with either, so there's no more current flow. It wants to go back because it perceives positive charge here, and it doesn't want to go forward because it perceives negative charge there, and like repels like. Okay, so how do you get around that? Well, what you have to do is that this barrier is more than just like the plastic coating on a wire. What you have to do is you have to have a negative ion go this way and a positive ion go that way. So the natural tendency to become positive here and negative there has to be countered by charges that either cancel out the negative charge or it has the negative charge simply migrate on its own. Now, these are not electrons and positrons, those are ions. So, so that would be like the zinc ion. Remember that the zinc electrode is corroding, and you can see it by eye. So you have zinc 2+, so the zinc 2+ needs to cross the barrier. And if it's zinc in solution, it's probably like an acid battery. So that's probably the electrolyte here, the liquid, is probably sulfuric acid. So the negative part, the negative would be like a sulfate anion, or if it's hydrochloric acid, it's a chloride anion. And you can also see why batteries are difficult to engineer. You have to be careful about the electrodes because often the solution is slightly acidic, and so that's going to corrode them regardless of the electrochem. It's kind of difficult to do. Okay, problem is the barrier. I'm just going to write that down. Is a problem. Okay, so if you could write this down, it's too much to write. A barrier that allows positive ions to go one way and negative ions to go another way. We have things like that, materials. One of them is called like Nafion, so Google it. But it's rare and expensive. So it turns out that having a semi-permeable membrane that allows both cations and ions to traverse, but no electrons, so it's permeable to like chemical ions, but not electrons. They're rare and expensive. So it turns out that's not a good way to engineer a battery. Instead, what you do is you use this design here, you use a salt bridge. Okay, and I have again, copper and zinc. And here's our voltmeter. And now you got yourself a really good battery. In fact, it's called a Daniell cell. And Daniell cells are, these are actually useful enough that people use them for the longest time. Up until like the 1950s, people they literally had these in various industries because they were so reliable. And they could be also scaled up and made very, very, very large. Okay, so let me tell you what's really going on here. The salt bridge has like some kind of gel, like agar or something inside of it. And so what it allows the ions, so what do we need? So this part, so the negative ions like sulfate go this way, the positive ions like go this way. So, and they exchange through the bridge. Okay, so what's happening here, by the way, there should be a little thing like that right now, looks better. All right, so what's happening is that basically, remember how, like resistance, so hopefully those of you who were into trying to learn electricity when you were younger, if you have like a strip and you measure the resistance, the further away you put your little probes, the more resistance you measure. So what you've done is you've taken the distance between the electrodes and you've made it way, 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 way wider. So that means that the electrons, for them to short circuit through the salt bridge, it's highly hindered because they have a long way to go. Or they could instead just go through the metal wire, and that turns out to be much easier. So they're going to prefer to do that. Another thing that happens is that due to the way charges collect, there tends to be what are called a little interfacial layer potential right at where the salt bridge touches the electrolyte in either cell. And these are called half cells now because the whole reaction is separated into two. So the two halves make a whole. That's the idea. It's kind of stupid. Regardless, there's a little bit of it's called a double layer potential, where the salt bridge touches the electrolyte, and so that also prevents, it works against charge flowing through them. I'm not going to test you on that, I don't really care. And so, yeah, with that, I should probably go ahead and hang out. I think I'm out of time.